So, hi, my name is Alex. I am a research assistant at Cal State Fullerton working under Professor Jeffrey Lovelace. And today I'll be telling you about a project that I've been working on with Dr. Neil Steppe from Caltech, which is SpECTRE's C++ tensor expression interface. And the goal of this project is to make it easier to read and write tensor equations in C++ and SpECTRE. So you just heard a bit about SpECTRE from Sierra, but generally, what it is open source numerical relativity code that's going to be used to solve different equations in different problems in astrophysics, and we're really excited about it. A couple of the use cases that we're really excited about in the future are simulating binary black holes as well as simulating black hole neutron star mergers. So in order for SpECTRE to do the physics that it's going to do, it needs to implement a bunch of physics tensor equations in C++ code. And to do this, instead of using some external tensor library, SpECTRE implements its own tensor code. And the reason for this is that other libraries don't have some of the features that we need to do general relativity. So for example, other libraries don't distinguish between spatial and spacetime indices, or they don't keep track of whether an index is up or down. But SpECTRE tensors do. And so we implement our own tensors. So what's the goal of our project within SpECTRE? So we're really excited about the physics that SpECTRE is going to be able to do. But we still have a lot of different astrophysical systems that we need to code up. And what this means is that we still have a lot of different physics tensor equations that need to be turned into C++. And the issue is that the process of writing these equations in code can often be tedious and error prone and take a long time. And so what the goal of this project is to make life easier for the developers by adding new tensor equations easier and faster and less error prone and easier to debug. And to better appreciate this motivation, I think it helps to see an example. So this is a small equation this is an equation that's a small part of computing the evolution of curved spacetime. And I just want to say that tensors are not matrices, but for the purposes of helping anyone who hasn't seen a tensor follow along, if you are not familiar with tensors, I just want you to picture this pi AB on the left as a matrix. So here, pi AB is a rank 2 tensor. It means that it has two indices, it's A and B. And just like a matrix, you can give a specific row and a specific column to get an element out. With a tensor, you can pick a specific value for the A index and for the B index and get a specific component out of the tensor. And tensors can have any number of indices, but this one has two indices. There's one other caveat to this equation. So again, if you're new to tensors, just know that with this equation, these two tensors that are being multiplied, the fact that we have this upper C index here and this lower C index here, it means that we actually have an implied summation over the values of C. So now we have our equation. Let's say now we want to implement it in code. What are the computational steps that we need to think about? Well, remember that this pi AB, if we want to compute pi AB, we have to compute all of these components, all 16 of them. So if we want to compute just one of them, where A is 1 and B is 3, that means that we're going to have this equation plug in 1 for A and 3 for B and compute that. But that's just for one component. We have to do something like this for all 16 of these. So in reality, it means that for all values of A and all values of B, we have to compute this expression. And so in code, what that looks like is we have to loop over the values of A, we have to loop over the values of B. For all of those, we have to compute this expression. So how do we compute this right-hand side expression? We have a sum over C, over the values of C, which means that we take this product for each value of C, plugging it in, and then we add them all together. So in code, what that's going to look like is for all the values of C, we're going to need to take this product, and then we're going to need to add them up. So the takeaway here is just that in order to code up tensor equations, what you're going to need is a series of loops. And depending on the equation that you're implementing, the loops will look different, but you're going to need loops nonetheless. So you don't need to pay attention to the specifics of this, but this is what this equation might actually look like in SpECTRE and C++. Now, writing these loops to implement this equation, it's not that bad, but it does take a little bit of thinking to write them and to read it if you were trying to figure out what equation it was. Now, what would be nice is if instead of these loops, we could write something like this, where the code actually resembles the equation. And also, all of this for loop stuff is kind of done automatically for us behind the scenes, so we don't have to think about it. So the idea here is that you have these variables pi up, g, and pi, and they refer to these three tensors. And then in the parentheses, you have their indices. This is a lot easier to read and to write as an equation than these for loops. Now, this isn't real C++, but with SpECTRE's tensor expression interface that we've now developed, you can write something pretty close to this, and it looks like this, where this single line of code will do the work of these for loops, and the code actually resembles the equation. So let's look a little closer at the syntax. So over here we have the left-hand side tensor, the pi. Here we have its indices, the lower a and the upper b. And then over here we have the right-hand side tensor expression. You can see the two terms, the g and the pi, and then in the parentheses, you see their indices. This TI underscore, those variables, they refer to generic tensor indices, TI standing for tensor index. And if the letter is uppercase, it means it's an upper index, and if it's lower, it means it's a lower index. And the last piece of this is this evaluate function. And what this evaluate function is going to do is it's going to do the work of all the for loops for you. And so all you have to do is write this single line of code, and you can call it a day. So if we go back to comparing writing this equation with the loops and then writing just this one-liner with the tensor expression interface, you might look at this and say, yeah, this is nice to write, but you know, the for loops aren't that bad. Well, here is some example code in SpECTRE that's part of computing the evolution of curved spacetime, where there are 4 equations that look similar to that example back to back. And you don't need to be able to see the details of this, but you can see that writing these loops can get very, very tedious very quickly. And being able to write them naturally with the tensor expression saves the developer's time, and it's a lot more concise. In addition, what if you were reading code and you got all these loops? Now, if I look at this, I don't immediately know what equation this is. However, if I saw this line of code, I can kind of read off an equation from left to right immediately. So if I read it, I can see, okay, I have LA equals RSA minus GKHKA times 1 plus T. Not to mention, if I had this equation and then I had to implement it in code, it's I have to think about the for loops and I might make a mistake and it takes some time. This is a lot easier. And all of these things that I'm saying are even more important when you consider that SpECTRE is implementing scary equations like this for the evolution of spacetime, for curved spacetime. Writing the for loops for this and reading them is not fun. So what can this interface do? You can, with tensors, you can do addition, subtraction, contraction, products. You can divide by doubles. You can take the square root of scalars, and you can transpose tensors, so change order of the indices. Also, it provides compile time checks, so of your math. So let's say that you wanted to implement this equation. You wanted to write it with this tensor expression interface. Now, let's say you made a mistake, and here you're supposed to put a C index, but you put A instead. The compiler would catch this error for you because you've repeated this A index here in this product. And if you think about that on paper, that's not allowed on paper. It's not mathematically legal. It would also catch that you have a C index on the left-hand side of the equation, but you don't have it on the right-hand side of the equation, which also isn't mathematically legal. So when you're coding tensor equations and then you're submitting jobs, waiting in a queue, and then also running long simulations, it's really nice that things like this can be caught at compile times at runtime. So what's the status of this interface? It's thoroughly tested. We try to test a lot of different cases. Compared to writing the equations with the loops, when we write them with the tensor expressions, sometimes the tensor expression versions are faster, sometimes they're slower. We want to look into why. When we write it with the tensor expressions, usually these equations compile in seconds, but we do have a couple extreme cases that take minutes to compile. We want to look into that. As far as documentation, the code is documented and publicly available, but we do want to add some tutorials on how to use the interface and how to write equations in a way that will minimize runtime. And just in case you are interested, if you're not working with SpECTRE on SpECTRE and you're interested in the technical details of this implementation, I'm just going to leave up these links. You can check out our documentation and the implementation at these links. And if you're really interested in the nitty-gritty details, I'm just going to leave these bullets up for you to check out and read up on your own. These are the details of our implementation. Thank you, and I'm happy to take any questions.